All right, let's talk about HPC workloads and how those apply to containers, right? So first of all, what does HPC, high performance computing, actually look like? And if you ask Wikipedia, it looks like this gorgeous data center of identical IBM machines as far as the eye can see. Or if you go to the Chinese Wikipedia, it'll show you this, the Tiana 2, this magnificent machine. It was the fastest supercomputer in the world until about a month ago and was surpassed by another Chinese supercomputer. In fact, if you just Google for high-performance computing and you look at Google Images, they all look like this, and it's beautiful. Have you ever been in a lab that looks like this? I've been in one, and it is pretty spectacular, but that's one in I don't know how many. Now go and talk to your newest college grad, your university new hire, or go and just talk to a university, and their HPC labs look like this. It's a bunch of PCs wired up, and this is a really clean, pretty one. This looks like the Beowulf clusters that I was building, a decade and a half ago. If you read the Slashdot to the Hacker News, I had no idea this was going to be set up, but here you go. You don't even have to look here. Look at at this setup, right? There's a lot of different ways of doing this. In fact, go and talk to your DevOps guy, and he's going to want one of these $20 an hour, $1,000 a day AWS machines, right? But in reality, when it all sets in, that's what a data center looks like, and that's what people are trying to use to crank out these calculations, do these high-performance computing type calculations. And other than being maybe a little bit disheveled, there's nothing wrong with that. I mean, if it works, it works, right? This is the reality of what most people are actually using in their day-to-day job. Now, what do all of those have in common? Because they're actually all quite similar. I mean, some are multi-million dollars and funded by governments. In some cases, it's built with a little bit of grant money. In other cases, it was probably built with a couple of $100 that someone won in a bar bet, maybe, right? But actually, they have a lot in common. There's a lot of things about all of those setups that are quite similar. First of all, they're all running Linux. All of the top 500 supercomputers in the world are running LinPack or some form of LinPack, some highly customized Linux, some Linux off the shelf. But you'll find that all of those are running some form of Linux. In fact, they're almost certainly running that Linux directly on the bare metal, installed on the bare metal to squeeze every IOP, every flop, every bit of performance that you can get out of that machine. And in doing so, you're trying to maximize that performance. You're trying to it's high-performance computing. You're trying to take huge problems and break them down by smaller machines, in some cases very large machines, and those are much bigger problems. And you're trying to minimize overhead. Overhead comes in a lot of different forms. It actually sneaks into all sorts of computing. We talk about big systems and small systems, big software systems. Overhead is all of the bits that are required around the solution to your problem to make the solution to your problem actually work, the software actually work. And then finally, and fundamentally, parallel computing, parallel processing, high-performance computing is about taking big problems and solving them using smaller units of compute, storage, and network, chopping up that problem into something that can be solved with smaller systems. Transcoding is a great example. I've worked with a number of different. It's kind of interesting to actually be here in a theater, a beautiful location. By the way, I'm going to show this to my wife. This is the projector I want at home. We need an upgrade. The transcoding is a fantastic example. You take this big video file, and maybe it's a 2-hour movie rendered at higher than 4K, and you're trying to render it down to 4K or 1080p or custom for your screen. It could also be many, many days of a security camera or something like that you're trying to transcode down. That's a great problem that's solved by parallel processing. You take that file and you chop it up into even increments. You spread it out to a bunch of machines. You tell that machine, transcode this to H.264, and you do the same, and you do the same, and you've got the first 10 minutes and the next 10 minutes and the next 10 minutes, and then in 10 minutes, you just put it all back together. Now, all of those also entail what really amounts to a clean environment. Your workload really wants a clean environment. It might be for security reasons. The previous speaker from Red Hat had some really good points around security, and a clean environment is essential to running one workload after another workload, perhaps on a shared system, a multi-tenant type system. And rarely are virtual machines used in HPC. Sometimes they are, and sometimes they're used for some of the management aspects. Certainly, it's nice to use virtual machines or virtual machine-like primitives. It's nice to be able to snapshot a workload like you can do with a virtual machine and move it from one system to another, maybe pause what's going on. That's very hard to do if you're running directly on the bare metal and not in a VM. But every time you run something in a VM, you're doing millions of these operations. And here we're measuring things in teraflops and petaflops, and we're talking about lots of these operations where the guest is actually running through a VM exit and then back into a VM entry, and doing that over and over and over again has a huge impact on the performance. We can reduce this a little bit with modern CPUs, but you can't get rid of this in the virtual machine world. And by the way, that clean room environment sometimes means rebooting the machine. Wipe the memory, reinstall the operating system perhaps if you're running really sensitive workloads one after another and tenants are actually untrusted. And has anyone ever pushed an EPO button? God, I've always wanted to. You have? Was it the most satisfying thing ever? It's got to be fun, right? Just, well, I haven't. One day, though. One day. So do that, and then you're going to have 1,000 machines in your cluster going through a boot process, which, we're very proud of how fast we can boot Linux systems. It's great to boot the kernel and systemd in 2 seconds, under 3 seconds, and we profile the heck out of that. But that doesn't matter when it takes 30 minutes to actually get to the point that the bootloader takes over and can run a kernel, because you're checksumming a terabyte of memory. You're scanning a huge iSCSI bus. You're, pixie booting or something like that. The time in between reboots is very costly, and ultimately it comes out to be just another form of overhead. Okay, so that's sort of the background. So let's look at why containers are a great solution. So we've talked all day today about containers for a lot of different types of workloads, the web-focused workloads, the developer-focused workloads, the functions as a service, the serverless workloads. And it's really great to see all of these points of view, and it's fun to see the same technology being used to solve lots of different problems. So first, let's talk about those process containers, right? I think this has been one of the best container events of any kind: Container Summit, Container Con, Container Camp, any sort of. This has been one of the best because I think this is one of the first ones where we have actually put really good taxonomy on the different types of containers. I think we finally internalized that and understood the difference between a machine container and an application container and a process container. And maybe that's not even all of them. Maybe there are more different types of containers and solutions that different container types solve. So when it comes to process containers, they're awesome for the HPC style function. The function that is calculate pi, right? Calculate the natural logarithm of some number or something like that. That's a function, and some of those have really efficient mathematical solutions, algorithms to that problem. And for those functions, you often don't need an entire operating system to run that container, and those are really well mapped to the Docker style of containers. And I borrowed this. I tweeted to the first talk this morning was from Craig from Google. Is Craig still here? Hey, there you are. Cool. So thank you for your slides. I needed to grab this piece out of it because it's, this is the sort of the Kubernetes way of doing things. And I would say one thing that you're going to see a little bit different in the way I discuss it is in this verbiage down here. But ultimately, Kubernetes is a really low overhead, really efficient way of scheduling these run to completion workloads. And we're working on the persistent workloads as well. But the run this job in a kubelet, do that lots of different times on lots of different systems. This architecture is fantastic for that. Swarm, Docker, and Swarm, Ben's talk this morning about Swarm was also really interesting, and this is his demo around around Docker and Swarm, I think captured it very well. I hopefully don't need to reiterate any of that, but it's really cool seeing that work its way into real solutions and real high performance solutions. So this is the DGX-1. It's from NVIDIA. It's a lot of money, but it's really cool in what it is and the size that this thing is. It's running Ubuntu, it's running Docker, and it's running workloads that are specifically packaged as Docker images, functions as a Docker image to run machine learning type calculations, cognitive computing type calculations. And that's a fantastic usage of containers and a really thin OS that kind of stays out of your way, right? Ubuntu is not the most interesting part of what's going on inside of that machine. It's actually, and Docker plus Ubuntu is that plumbing layer. What's actually interesting is the ingestion of petabytes of data and what's done with that data inside of the system. In a different form of supercomputer, you'll see something like the IBM Linux One, the Z series mainframe. This is mainframe 50-year-old technology coming back to an all Linux system from ground up. And there we see a lot of Ubuntu and Docker and LXD containers running inside of these IBM mainframes. And so the other way to look at it, or another way to look at it, is from a machine container perspective. And these are the replacements for virtual machines. They look like a machine, but it's actually a container. And one word that sticks in my mind, and in fact it's kind of a code word that we end up using when we run containers, not containers plural, but run container, singular. When we run one container, LXD container, on the bare metal, we call that an alloy container, an alloy mode. So an alloy is a blending of different metals to make a metal that's stronger, has stronger characteristics. And that's sort of what we do, sort of exactly what we do when we run one container on the hardware and we meld that bare metal and that container into one thing. So we often use this diagram to show what LXD looks like on you got a bunch of hosts and you've got a kernel, and then we've designed LXD to be a hypervisor. We've implemented all of the hypervisor functionality that you would find in a KVM or a Xen or a VMware is present in LXD. There's remote APIs, there's tools that can talk to that REST API, and we typically talk about how many containers we can run. We can run 10 to 20 times as many LXC containers on a system as KVM virtual machines. But actually, if instead of running a bunch of them, we run one, exactly one, and we give that one container full access to all of the CPU, all of the memory, all of the disk, all of the network, all of the I/O available, it's like having all of that machine, but being able to take advantage of all those management aspects you get out of containers and VMs, the live migration, the snapshots. So we'll dive into each of those. So with LXD, you can tune up or down any of the number of cores, the number of CPU cycles, the percentage of the CPU, the amount of memory each container has, the disk space, the disk I/O, and the network I/O. So when we're launching LXD containers in an OpenStack and we're giving little slices of compute, we limit how much can be done, right? But there's a tunable in OpenStack which allows you to create flavors. A flavor is an instance size. It's like an Amazon T3 micro versus a M3 extra large or something like that. And we can put those boundaries on LXD machine containers to limit them. But if we take those off and instead we say we're going to give one container priority and only one, exclusivity on that hardware, you can really create an interesting HPC system. Exclusive access to system resources is really what that boils down to. But it still contains the security aspects, the security features that you have around containers. It's separate from the hardware, right? One of the most dangerous things you can do when you give someone physical access to hardware, you can go and ask Rackspace and SoftLayer. They've built a ton of tooling around flashing the BIOS between every different tenant that uses that hardware, because you can inject some really nasty malware that's hard to detect at the OS level into the BIOS, and so that's typically wiped. Well, in a container, if you're running as root inside of that container, you don't necessarily have access to something like the BIOS or the firmware. And so we use a combination of four things to secure containers. Again, I think it was Chris, the Red Hat architect. Are you still here, Chris? No? It's too bad. He had a great slide that showed C groups, namespaces, SE Linux as the way Red Hat secures containers, and that's pretty much exactly how we do it with the replacement of AppArmor. We use AppArmor for the mandatory access control, user namespaces for the discretionary access control, and C groups. We saw a presentation from, I think it was Liz earlier today, about user namespaces. User namespaces is what ensures that root in the container, that can do anything they want to do inside of that container, is not root outside of that container. C groups is the resource control, but also the grouping of the processes, that illusion that Mark talked about. That's handled by C groups. AppArmor is what ensures that a malicious user who's able to take over code, running code in the system, elevate their privileges, escalate their privileges, is not able to do anything else that process wasn't initially allowed to do, right? And that's super important. That's mandatory access controls. Raise your hand if you've ever, I'll do this again, like Chris said. Raise your hand if you've ever disabled SE Linux. Yeah, okay. Raise your hand if you've ever disabled AppArmor. A lot fewer. So one thing that we've done with AppArmor is we tried to make it we tried to keep it out of your way. It's securing you. Every Ubuntu machine that you've ever turned on is running AppArmor in enforcing mode. But we've done it in a way that hopefully it stays out of your way, and you rarely have to disable AppArmor. I'd be very interested in learning the situations that you had to disable AppArmor. Seccomp is a very sharp, very small scalpel. It's a way of carving out certain system calls from a given process and allowing or disallowing a process to run those sys calls. And it takes a fine-grained policy. It's really powerful when you need to customize what a container is able to do. So containers are awesome instant startup. You don't get that out of that bare metal supercomputer that you have to reboot, right? But you can provision a container on that system in seconds, like 2 or 3 seconds. It looks like a machine. It looks like a machine, and it's really efficient because it's Linux on Linux, right? We run a lot of KVM instances where we've got Linux running in the KVM and Linux running on the host, and that's great. That's a great Linux on Linux setup, but it's super wasteful, right? If you've got 50 virtual machines running on a given host, you've got 51 kernels running on that system, consuming CPU cycles, consuming memory. Sure, you can dedupe some of that, but not all of it, and it gets fragmented. If you've got 50 containers running on that same system, you've got one kernel, one copy of that kernel, and lots of different OSs that you want to run there. That's also important from a security perspective, in that you only have one kernel to update, right? Instead of 51 kernels to go and update, which might be on all very different levels. There's no more efficient way to do Linux on Linux than containers. And if you're looking for a machine, then machine containers. Zero latency, that process is actually running on the underlying CPU. So there is no VM exit portion. That process is being scheduled just like all the other processes. And so you can set the priority accordingly or let the kernel take care of that. Overhead is negligible. It's essentially zero overhead. It's just another process, but it's wrapped up in a nice way. And the performance is identical to running that on the CPU, with the added benefits of snapshot and restore. You can snapshot a container and restore it later. And in some of the HPC environments that I've been in, especially in the oil and gas industry, there are workloads that get paused because it's a multi-hour, multi-day. They're lower priority. They're paused, while another workload preempts it, is loaded, runs quicker perhaps, and then is moved off, and the other workload's able to come back. That's possible through snapshot restore, and live migration is also part of that, being able to rearrange where those workloads are running from one system to another. There are some constraints around live migration. It takes hardware that's very close to identical to be able to work, but in those really pretty data centers, that hardware is all pretty much identical, right? So I've got a demo. I've got, I think, a couple of minutes left. So let's take a look at some of this. So I've got a cheat sheet down here that's just going to keep me from fat fingering anything, and I'm just going to copy and paste across these splits. So I'm going to launch a container. It's called Container Camp. That launched in 2.5 seconds, and that launched all the way to the point that machine has actually drawn an IP address. I could have bridged to the network, but I think that might have upset some people. So I'm drawing an IP address just off of a DNS mask running local. If I run PS inside of that container, I'm going to make that just a little bit bigger. This is what Mark showed earlier. Trust me, it looks like a machine to any process that would normally be running in a physical or virtual machine. Running inside of LXD, it doesn't take any retooling. We love and we use extensively Docker and Kubernetes for the microservices, the new architectures, the new software that we develop. But we've got a lot of software that we can lift and shift and put into a container and do it more into a machine container and do it more efficiently without rerunning anything. A little bit of testing, and then it's off. You're off to the races. The network looks just like the network on a virtual machine. It draws an IP address. I can bridge that out. The disk storage, is tweakable. I'm going to import my SSH key here from GitHub. I'm going to SSH into this machine, and then SSH is going to let me into this machine, and now I'm doing everything that we were doing before. That's because an SSH daemon is running. I can treat this just like any other system, any other virtual machine. So from a performance perspective, I'm going to run. You can do lots of different performance benchmarks. This one's convenient because it takes just a couple of seconds to run, 3.5 seconds. I can run it again. I'm running sysbench. I'm telling it use my CPU and use all four of them, all four threads on that CPU. And if I run that same command inside of first I'm going to have to install it, sysbench inside of that container. But if I run that same command inside of the container and tell it use all 4 CPUs, because this container I set up unbounded, it takes 3 seconds and change, right? Identical performance. We'll run it again just to make sure. But we can also set those limits. So I'll set and unset those limits. So first of all, we're going to see that we have what looks like 4 processors inside of that container, and I'm going to limit it to just one. I'm going to say, sorry, you only get one of those processors, and so I count them now. And now I'm going to run that same benchmark, and I'm saying run 4 threads of this on one CPU. What's that going to take? 4 times as long, right? Awkward silence, and yeah, that took almost 10 seconds here. Of course, I can set that back and give this back to having unlimited access, basically, to the CPUs. Beyond the CPU count, I could also set that percentage of CPU. Setting the memory might also be interesting. So at this point, this container has 16 gigs of memory. I'm going to drop that down to 128 megabytes, and we'll see now that that container is down to 128 megabytes. If I wanted to end this presentation short, I'd go and run something in here and that container and then blow it up and then start another one, right? But hey, this talk is about HPC, so I'm going to go back to giving that container all of the memory. This one's interesting. Let's kick off in the background a big wget. I guess we could have streamed Netflix as well. And you'll see that we're getting actually quite slow bandwidth. I was getting multiple megabits there earlier. I can limit the ingress to a single megabit. Maybe I forgot to unset that because I was expecting it to go a lot faster. Or I can increase it and give it full access to all of the network. It's a lot more dramatic when you're plugged in and on a gigabit network. You'll see a huge difference here. So forgive that part of what's going on here, and we'll blame it on inconsistent networking. And then finally, from a snapshot perspective, I'm going to snapshot that container and call it backup 1. I'm going to do something absolutely horrible to that container. I'm going to RMRF all of user and bin, and then I'm going to say, yeah, and I want to run bash. And it's going to tell me, sorry, you can't, because that container is completely hosed, right? Completely useless at that point. But the good news is I can restore that container in a matter of seconds. And now I'm back into that container. It's exactly like it was. The snapshot restore is part of the CREU project and exactly how we live migrate. I've only got a single machine here, and so I can't live migrate. But if I had 2 machines sitting right next to one another, I could type LXC move from my laptop and the name of that container to another system that's running LXD, and it gets moved immediately. All right. I think that's all I have here. Well, thank you very much.